In this video, I'm going to talk about some real-life applications of contour maps and level curves and stuff like that. And my examples are all going to be drawn from earth science in different ways here. And I'm going to have 3 different types of examples. So take a look here. This is my first example here. We're going to be talking about contour maps in terms of elevation. By the way, to give credit, I stole this picture here from the retailer REI. They do lots of outdoors stuff. I think the next one's from REI as well. And so the idea is that we can think of elevation. We can think of elevation as a function of 2 variables that say your latitude and your longitude give you, input is latitude and longitude, output is your altitude, your elevation above sea level here. And so instead of trying to draw mountains and stuff like that, going up and down, whatever, that will make a very difficult map to read. Instead, what we're going to do is that we're going to draw contour maps, elevation maps here to show how far above sea level you are. So take a look here. These are both representing hills and mountains. And so the idea is that if we have this hill, or I guess this is more a steeper mountain, this is more of a shallower, gentler hill here. The elevation at different points here is going to be represented in this contour map. And so let's see, this contour is labeled 1440. Let's say it's being measured in feet. So walking along this curve, you're at 1,440 feet above sea level. Walking along this curve, you're at 1,440 feet above sea level. Taking a look over here at the key, the next one is 1520. So walking along that curve, you're at 1520. Walking along that curve, you're at 1600. Walking right there, you're at 1680. At the top of the mountain, somewhere between 1680 and 1760 feet above sea level. And this one over here, it tops out over, like 1840 feet right there. Comment to make here, steep slope versus gentle slope. We can see that from the pictures here. How can we tell that from the contour map? So the closer together contours equals steeper slope. And then contours that are more spread out so this would be a, slower increase. Slower increase and a gentler slope. Okay, so here's another thing here. 3D views. This is getting after the same thing here. This 3D view here, this isn't an efficient way to. This would be the graph, I guess, or the surface. Back in the last video, that terminology, but this isn't maybe the most efficient way to communicate information. We can't see what's on the other side of that mountain there. This allows us to communicate the information more efficiently. I borrowed this one from Penn State's website here. Don't know if geography whizzes can identify the shape here. This is an island. This is actually a contour map for the big island of Hawaii. 2 volcanoes here, Mauna Kea and Mauna Loa. Those are 2 of the largest volcanoes in the world here. Let's analyze what's going on. We can see that, the contours, contours every 1,000 feet. So this is sea level. That's the beach. 1,000, 2,000, 3,000, 4,000, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like 14 or 15,000 feet. It's a little bit hard for me to read here when we get close to the top, but we can see this is this contour map shows us that this is a mountain, and this is also a mountain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, again, somewhere between 14 and 15,000 feet, if I counted that correctly. So the contours here show us that there's two mountains as we go up here, with a valley at about 6,000 and change feet in between those two mountains. Also, going back to the steepness and more gentler slope, if we were to do this right here, look how closely together the contours are. So closely spaced contours. This is very steep. So hiking up that would be a real challenge to do that. That would be very steep. Also right there is very steep. Also right there is very steep. Here going up, this is going to be more, the contours are spread out farther. So this is less steep. That would be a not steep. That would be a not steep way to do things here. And so, again, these contour maps, they capture a lot of information here. Obviously, it's a little bit silly for me to suggest that you could, like these are very big distances here, but it does capture the idea of, this contour map, which is capturing level curves. Remember, the idea here is that everywhere on this level curve, you're at 5,000 feet above sea level. That's what's going on here. It tells you a lot of information here about how to hike this. It communicates lots of information. Okay, so I promised 3 different applications here, all from earth science. So the first is like this topography, elevation kind of maps, and this is very important. Now let's go over to atmospheric sciences. So this right here, and I borrowed this from National Weather Service's website. This is a map of the U.S. with some temperatures, and let's say it's Fahrenheit superimposed on it. And so the idea here is that everywhere that we see along this curve, this is all at 30 degrees Fahrenheit. This is all at 40 degrees Fahrenheit. That's all at 50, 60. Again, this is showing us contours of equal temperature here. And so this allows us to see things like this is going 40 to 30, 20. This is less than 20 in there. So this is like, this is cold air in here. There's a big little bubble of cold air. And this is warm down here. And note here, this is some kind of big front. There is a rapid temperature change going from here to here, going from Missouri, it's below 40 to, down here in this part of Mississippi, it's above 70. That's a very steep temperature change in a very short amount of distance here. That probably means there's a storm there. The fact that those are so close together might mean that there's a storm there. If I'm wrong, don't hold that against me, but, I'm certainly not a meteorologist by trade, but this gives us some information here from this temperature contour map. So we would call these an isotherm map. The contours we call isotherms here, again, gives us lots of information. One final picture here, and sorry, this is a little bit hard to tell, but I wanted to go for a little bit of historical significance here. This is actually atmospheric pressure. And this, again, I borrow this from National Weather Service. This is actually a picture here of contour. So the idea here, there is some kind of, we're thinking about pressure at sea level here. What is the atmospheric pressure here? And this, see that there's all of these concentric circles right here. This is actually the worst storm I've ever lived through in my life. This is a real-life map from Hurricane Sandy hitting New Jersey and other Mid-Atlantic, the rest of the Mid-Atlantic region back in 2012. And so the idea here is that you have, if you can read here, 10, 16, 10, 20, 10, 16, 10, 12, that's something to do with air pressure. There's something to do with air pressure. Note that 1008, 1004, 1000, it's going to quickly get down to 996, 992, 998, 984, 980, 976, and the air pressure plummets as you get closer and closer and closer to the center of the hurricane. And that's a very characteristic feature of hurricanes, is that they're going to be very low pressure at the middle, in the eye of the hurricane. It's going to be very, very low pressure. And once again, we see here that the contours are very, very closely spaced together. And pressure changes, again, I'm oversimplifying things here. If you're a meteorologist, don't hold this against me, but temperature changes, sorry, not temperature, pressure changes is what gives you wind. And so if the pressure isn't changing very rapidly here, the wind isn't going to be that great, but this is how you end up with well over 100-mile-an-hour winds, is because you have very, very, very rapidly changing pressure. And we can tell that the pressure is rapidly changing as you move along because of how closely together spaced the contours are. And so by looking at this, you can tell the wind speeds are going to be very, very great. And of course, for anybody who lived through Hurricane Sandy, you know that, yeah, it was a very, very, very windy storm. So again, let's not lose sight of what's going on here. We can think of atmospheric pressure at any given point, right here in Columbus, Ohio, as a function of two variables. Think of the latitude and longitude of Columbus, and the output there is the pressure at Columbus, pressure at that point. And this kind of map summarizes all of this information about pressure, and it can really let us make, do some very nice real life interpretation. Say, there's a storm there. It's going to be very windy. That's a very bad storm. Okay, so hopefully this video here was instructive, and I think that for a lot of what we're going to be doing in this class, thinking about things with this kind of pressure or temperature or elevation, it allows you to really get a better picture for what's going on.